So today we will look at the consequences of the heat conduction inequality. Conduction inequality. So we saw that this basically the inequality was given by Q naught dot G naught is less than or equal to 0. So we will see the consequences of this particular inequality. But for that, we will introduce what is known as the conductivity tensor. So there is K of E comma theta naught Ij is equal to minus del Q naught I by del G naught J. So this is evaluated at E theta naught G naught evaluated at G naught equal to 0. So so basically you first take the derivative of del the flux with respect to the temperature gradient. So that is the ith component of the flux with respect to the jth component of the temperature gradient, and so that will form the ijth component, and you evaluate it at Q naught equal to 0. So this is similar to what we did in the case of linearized elasticity, where we evaluated the elasticity tensor about f equal to I, the reference configuration. So this is somewhat similar to that, because this will help us in linearizing this particular equation for the flux. So one thing to note is that K is not necessarily symmetric. Not necessarily symmetric, except if you assume, so except in special cases, so if you assume it to be isotropic or things like that, then of course it will turn out to be symmetric, but in general it need not be symmetric here. So if we now fix E and theta naught, so fix E and theta naught, and then you expand about G naught equal to 0. So expand about G naught equal to 0, then you will get that Q naught as a function of G naught is equal to Q hat naught evaluated at G naught equal to 0 minus K times G naught plus order of G naught. That is so we are just doing a Taylor series expansion of Q hat naught. Now substitute this into the inequality that Q naught dot G naught is less than or equal to 0. So you will get that Q naught at 0 dot G naught minus G naught dot K times G naught plus order of G naught square is less than or equal to 0 for all G naught. Now, so what you do is that now you let G naught be small in magnitude. So what will happen is that this term will dominate all the remaining terms here, right? So because G naught is small in magnitude, and then if you switch the sign on the G naught, you will see that this inequality is violated, right? And so the only way that this inequality is not violated is if Q naught of 0 is equal to 0. Okay, so this implies, so basically this implies that Q hat naught of 0 is equal to 0. So this is of course a very intuitive prediction that if the heat flux vanishes, if the temperature gradient vanishes, then the heat flux also vanishes, right? So that is a very intuitive conclusion that you get. Now if you take this to be 0, then you will see that again now let G naught be small enough such that this term dominates all the remaining terms, and then the only way that this can be satisfied is if K is positive definite, positive semi-definite. So G naught dot K G naught is greater than or equal to 0 for all values. So basically these are the two conclusions that follow from the heat conduction inequality. So let us just write that down here. So theorem, the heat flux vanishes whenever the temperature gradient vanishes. That is Q hat naught of E theta naught 0 is equal to 0, and K of E theta naught is positive semi. Because as a result of this particular theorem, we can write the first approximation. So first approximation, we can write Q naught of E theta naught G naught is equal to minus K E theta naught times G naught. So this is like a linear approximation. So this is known as the Fourier law of heat conduction. So this is known as the Fourier law of heat. Yes. So if you have an isotropic material, so that would be a special case of this. So as I already remarked that K need not be symmetric, but in the case of an isotropic material, we will have a simplification. So for an isotropic material, you will have Q is equal to minus K of theta times G, and in that case, you will get that K is equal to K times theta naught of under root of del C times C. So this is after you transform all the variables using the PLR transform and all of that. After you do all of that, then you will get this K as equal to. So this is the second order tensor, and this is just a scalar actually. So this is small. This is a small K. This is the capital K. You will get this particular transformation rule between the small k theta naught and the capital K, which is the conductivity tensor here. So in this particular case, you can see that the conductivity tensor is symmetric. This C is the right Cauchy-Green stretch tensor here in this particular case. We will, in order to simplify the energy equation, now we will introduce what is known as the specific heat and the latent heat tensor now. So define now. So let C of E comma theta naught be equal to del E hat by del theta naught. So this is evaluated at E theta naught, and this is called as the specific heat now. So that is just the gradient or the derivative of the internal energy with respect to the absolute temperature here. And we have a relation between E and the free energy. So we can use that to express this specific heat in terms of the specific entropy. So let us do that now. since E is equal to psi plus eta theta naught, so you'll get that del E by del theta naught is equal to del psi by del theta naught plus eta hat plus theta naught times del eta hat by del theta naught. But we have already shown that eta hat is minus del psi by del theta, right? So this actually goes away since eta hat is minus of del psi hat by del theta naught. So this we saw was a consequence of the second law of thermodynamics. In the last class we saw this, and so this can be written as theta naught times del eta hat by del theta naught. So this so we can write now the specific heat in terms of this particular quantity here. So basically now what you have, so this implies now that C of E comma theta naught is equal to theta naught times del eta hat by del theta naught. And so this is an expression for the specific heat in terms of the specific entropy. Similarly, we will also define what is known as the latent heat tensor. So the latent heat tensor H. So H is equal to theta naught times del theta hat by del E, and that is equal to minus theta naught by rho naught times del S tilde by del theta naught. So that is because we know that eta is minus del psi by del theta naught, and we know that S is rho naught times del psi by del E. So using that particular relation, we can also express this latent heat tensor, which is the second order tensor, in terms of the specific entropy or in terms of the second order of stress. Fine. Then now we can simplify the energy equation. So if you recall, we have already derived the energy equation. So that is now rho naught times del eta by del T times x is equal to rho naught times QH naught minus del dot Q naught. So we derived this in the last class, and so we said that a process is isentropic if and only if it is adiabatic, right? So if you recall, this was a relation that we derived in the case of the thermoelastic material. So now apply the chain rule to this one. So you will get that this is equal to rho naught times del eta by del theta naught times del theta naught by del T plus del eta by del E times del E by del T. So this is a matrix in a product here times so this is all evaluated at capital X. This is equal to rho naught QH naught minus del dot Q naught. And we have seen now that the C is theta naught times del theta by del theta naught. So we can use that to simplify this particular expression here. So you will get that rho naught times C times del theta naught by del T plus H times plus H matrix inner product E dot is equal to del dot K times G naught plus rho naught times QH naught. So just by substituting the given results here, you will get this particular result here. I think I may have missed out a theta theta naught here. So let us just see theta naught. So theta naught times del eta by del theta naught. Yeah, there may be a theta naught here. So there should be a theta naught here also. So so theta naught times del eta by del theta naught, that will give me this c here. So that is the c times del theta naught by del t plus, and then this theta naught times del eta by del e is this h, and so h times e dot. So now it is correct. So there is a theta naught that was missing here. So just introduce that here. This is the simplification that we get in terms of the specific heat and the latent heat tensor now. In addition to the, so suppose if you are solving a thermoelasticity problem, so in addition to the balance of linear momentum, you would also need to solve this particular equation, because see, now the temperature field is an additional variable, right? And so since the temperature field is an additional variable, you need an additional equation to solve for the temperature variable, and so that additional equation for the temperature variable is provided by this particular equation here. So just to give an example now, so basically let us give the various tensors for a Sag-Anapic material here. So let me present all the equations for the Sag-Anapic material. So for a Sag-Anapic, so let alpha be the coefficient of thermal expansion. C had this specific heat is assumed to be a constant, so C is assumed to be a constant, and you will get that xi hat now in this case is given by 1 by 2 rho naught times lambda trace of E times square plus 2 mu times E matrix inner product E minus H matrix inner product E times theta naught minus theta reference divided by theta naught plus C times theta naught minus theta reference minus theta naught log of theta naught by theta reference. This theta reference is like the room temperature, the ambient temperature. So remember, theta naught, the naught does not indicate that the ambient temperature. So theta naught is actually the absolute temperature. But just I am putting the naught there because we are expressing it in terms of the reference configuration coordinates, and so that is the only reason that that naught, the theta naught is being put, because this is, but this is actually the temperature, the actual absolute temperature here. So the reference is the ambient temperature, the room temperature, and so this is the model that you have, and then now what you will get as the second derivative of stress from this is S is equal to lambda trace of E times identity plus 2 mu times E minus 3 kappa alpha, 3 kappa times alpha times theta naught minus theta r times the identity tensor. So this is obtained using the relation that del xi, S is rho naught times del xi by del E. So that is the relation that we have. So actually, I mean, it may not be obvious where the alpha comes from. The alpha is actually coming from this H here. So let me write that H is equal to minus theta naught by rho naught times del S hat or del S tilde by del theta naught, that is equal to 3 kappa alpha theta naught divided by rho naught times the identity tensor. So you will see that this when you combine this H with E, you will get trace of E in that particular place here. And then once you take the derivative of trace of E, you will get this particular expression, whatever I have written here. So, so this is just a direct consequence of using S is equal to rho naught times del xi hat by del E. So this is obtained just using S is equal to rho naught del xi by del E. So that's just by differentiating it, you will get this particular expression here. And so this is the latent heat tensor, and the entropy function and eta hat will be equal to 3 by rho naught times kappa times alpha times trace of E plus C log of theta naught by theta r. So this is what I mentioned in the beginning. So when we started this discussion of the second law of thermodynamics, if you recall, when we used the Clausius-Duhem inequality, at that time I mentioned that the entropy function is not defined in an explicit way. We just said that there exists a function, an entropy function that satisfies the Clausius-Duhem inequality, right? So that is how we had said, and then at that time we had said that the actual computation of the entropy is through a constitutive specification, right? And so here you can see that for the case of thermoelasticity, we are specifying the entropy function through a constitutive relation. So in each case, so basically there is no specific definition of the entropy. The definition of the entropy or the actual computation of the entropy is carried out through a constitutive relation, just like in this particular case here. And so this kind of a specification will of course differ from material to material. So suppose this is the specification for a cyanide type of material. For a rubber type material, it will be something different. For a fluid, it will be something different, and so on and so forth. So basically the computation is done through a constitutive relation, and the important thing to remember here is that the constitutive relation that we use for the entropy function should be consistent with the second law of thermodynamics. So we have to use all the inequalities that come out of the Clausius-Duhem inequality. So those should all be respected while formulating a constitutive relation of this particular kind here. So here this kappa is the bulk modulus. So kappa is lambda plus 2 mu divided by 3. This is the bulk modulus. And so this is the model that you get. And the heat conduction equation in this particular case will be heat conduction equation will be given by rho naught times C times del theta naught by del T, keeping capital X fixed, plus 3 alpha times kappa times theta naught times trace of E dot is equal to del dot K times G naught plus rho naught times QH naught. So as I said that this is the additional equation that you would need to solve in order to so this is the additional equation you would need to solve in order to solve for the temperature field. But you can note that actually the balance of linear momentum and the energy equation are going to be coupled, in the sense that, see, your second Taylor curve of stress depends now on the temperature, right? And so basically when you write the balance of linear momentum, there are terms that will involve the temperature. So so the balance of linear momentum will involve terms that involve the mechanical deformation and also the temperature. Similarly, if you now look at the heat conduction equation, that involves the deformation through E dot. Correct? So that's why. So actually, it's a fully coupled problem that one needs to solve. So here, I mean, this is not involving only temperature. So suppose if you ignore this particular term here, this E dot, so that means many times that assumption is made that you are ignoring the deformation of the domain because that may be small or whatever in the energy equation. Then in that particular case, it will be a one-way coupling. One-way coupling means that then the deformation of the domain is not influencing the temperature, and you can first solve for the temperature and then substitute that into the balance of linear momentum to get the stresses and the displacements and so on. But if you don't make any approximation, then it's a fully coupled problem, and so you will have to solve it as a fully coupled problem. That means the displacements depend on the temperature also depends on the displacements, and so it is a fully coupled problem that one would have to solve here. Yes, and then now let us come to the justification for a hyperelastic material. So I already mentioned that there is a thermodynamic justification for assuming a material to be hyperelastic. So now let us look at that particular justification here. So for an isothermal deformation, you can take W hat of F is equal to rho naught times del xi hat of F, because we have seen that xi depends only on F and theta. But if theta is a constant, then it depends only on F. And so you can take the strain energy function to be simply the free energy. Right? So and in that case, just if you take the gradient of this, rho naught is just assumed to be a constant. So if you take the gradient with respect to E, then you will get the second period of stress here. So this is one case where the deformation is isothermal. Similarly, if you now write for a isentropic deformation, so you will get that E hat is equal to xi hat plus theta hat, theta naught, and so you will get that del E by del theta naught is equal to del xi by del theta naught plus theta naught is equal to 0. Right? And so if you have an isentropic process, so here we have assumed that eta hat is a constant here. So this is so that is why there is no derivative of eta with respect to theta naught. So for an isentropic process, so for an isentropic process where the entropy is a constant, this is equal to 0. So basically this is that E hat is equal to E hat of F. No, there is no dependence on theta here. And then in that particular case, you can take the W hat of F is equal to E hat of F. So these are the two cases where you can assume that a material is hyperelastic. So this gives a thermodynamic justification. So if you see the purely mechanical theory, right, as I already mentioned, that generally if you take any elastic material, people will always assume it to be hyperelastic also. And so this gives the justification for why they do that. So typically you will see that immediately they will write the strain energy density function for a material. So in principle, a material can be elastic but not hyperelastic. But as I said, that typically we always make the assumption that if it is elastic, we automatically assume it to be hyperelastic. That is the reason is here that at least under isothermal conditions, you can definitely take it to be hyperelastic, right? Because you can take the strain energy density function to be the same as the free energy. In case it is isothermal, and you can take it to be the same as the internal energy in case it's an isentropic process. So at least under these two assumptions, one can definitely assume that a material is hyperelastic. Yes, so then, so this is one approach to thermoelasticity. So actually, maybe I should mention that there are other approaches to thermoelasticity also, based on a split of the deformation gradient into an elastic part and a thermal part and so on. So it is not as if this is the only theory for thermoelasticity that is existing. There are other theories. See, whenever the nature of the material model is complicated, then it is not clear exactly what material model to follow, and so all these different models arise because there will be some shortcomings in whatever is being used, and they try to fix that. But of course, they will also have their own shortcomings and so on and so forth. So all I'm trying to say is that there are various models for thermoelasticity also, and you can take a look at the literature in order to find the other models. But let me just say that this model, whatever I have written here, is probably the most widely used model in the literature here. The other models are based on the decomposition of the deformation gradient is not so very widely used. Okay, so that sort of completes the discussion on thermoelasticity. So now we will turn to a discussion of fluid mechanics now. So basically, again, we are going to carry out this exercise of looking at the restrictions imposed by the second law of thermodynamics and material frame indifference on the constitutive relation for a fluid. So let us look at that now. Okay, we'll start with that now. So fluids. So I will explain what I mean by short-term memory, but first let me just write down what are the constitutive relations that we are going to assume here. So f theta g dot and the tau is equal to tau hat of f theta g dot and then eta is equal to eta hat f theta dot the q is equal to q hat of f theta g f dot. Okay, so let us now see what we mean by short-term memory here. So here basically, see, we have seen that the response function will depend on the history of the deformation gradient, right from minus infinity to the current time, right? But here we are taking only f dot. So if you think of f dot as limit of f of t minus f of t minus delta t as delta t tends to 0, right? So basically you are looking at only very short term memory effects here, so which are captured by this f dot. So basically this will only capture the behavior of fluids that have only short-term memory. Okay, so fortunately we will see that includes all the Newtonian fluids, right? That means like air, water, and so on. But it does not include some other types of fluids, the non-Newtonian fluids, such as polymer solutions or blood, and so on and so forth. So it is very important to remember that whatever analysis that I am going to do is not valid for arbitrarily for any fluid. It is valid only for fluids where only a short term memory of the deformation gradient is playing a role in the constitutive relation. So, as I keep repeating that your list of kinematical variables has to be accurate. Otherwise, it will not model the given phenomenon correctly. So, if you try to use this particular model for modeling a polymeric solution, then it will give incorrect results, because for a polymer solution, you have to take into account a longer memory of the deformation gradient, right, and a longer history of the deformation gradient. And this F dot is simply not able to capture this long term history of the deformation gradient. And so, as I keep repeating that if your list, so the list of these kinematical variables that you are using for the constitutive relations is critical. If that list is incorrect, then all your results are going to be incorrect. Okay, so so then you may ask that how does one fix this list of kinematical variables? So that is based on physical experience, right? And so basically you have to carry out experiments on that particular material and see whether you know what kind of history dependence it has, and so on and so on. It's a very complicated process, and so that is the reason that actually we do not even know exactly what the constitutive relations are for non-Newtonian fluids and so on. So people just propose different types of models, but none of them are satisfactory. But at least for air and water, we will see that this works perfectly. Okay, so, and so this gives a very, very accurate description of Newtonian fluids. As I said, air and water constitute maybe perhaps more than 99% of the fluids on Earth, and so very, very fortunately, this kind of a model is good enough for modeling at least the air and water, which are the predominant fluids. And we'll see that actually in these cases it's a very spectacular success, as we will see here. Fine. So we have not defined exactly what we mean by a fluid. Okay, so physically, let me give you a picture. So suppose if you have a fluid in a bucket, and then now you take some water in a test tube, let us say, and then test its properties. Okay, so you are just taking the fluid from the bucket and you're putting it into a test tube and then conducting some experiment. So basically, if the even if the fluid undergoes a density preserving deformation, even then the response of the fluid remains the same. Okay, so this idea is in some sense a generalization of the concept of isotropy. Okay, so in isotropy we saw that tau hat of f is equal to tau hat of f cubed. So basically here we saw that we are rotating an object and then applying the same deformation gradient, and then now the stress is the same, right, in this new direction also. And so this was valid for all q. Right? This was valid for all q belonging to R plus. Now, in the case of a fluid, we demand something more now. So what we say is that even if it undergoes a density preserving deformation, the response of that fluid remains the same. Okay, so that is the way we will define it. So here, in this case, we define it as tau hat of f is equal to tau hat of fh, where this h is what is known as a unimodular tensor. So this h is a unimodular tensor. So that means determinant of h is equal to plus 1. So this is valid for all h, which are these unimodular tensors. So unimodular tensor is determinant of h is equal to plus 1. So where does this condition come from? So basically this condition comes from rho naught is equal to rho tilde times j. Right? And so if it's a density preserving deformation, then that means your j is equal to 1. Right? And so in that case, basically we are looking at deformations which will give. So now you can see that this is a density preserving deformation, because determinant of fh will be equal to determinant of f itself. Right? And so in that sense, it's a your j, which is determinant of fh, will be equal to the determinant of f itself, and so that is why it's a density preserving deformation here. So we'll use this particular definition for this fluid here, and so if I now write H, so if H is equal to, so we'll make a special choice of H so that we are able to reduce these constitutive relations in some sense here. So let us write this H as j raised to 1 by 3 times f inverse. So you can see that this determinant is equal to 1 here. So if I make this particular choice, so this implies that determinant of H is equal to plus 1, and if I make this particular choice, then so you can see now that if I substitute this H is equal to j raised to 1 by 3 times f inverse, then this reduces to a dependence only on j, because f times f inverse will go to the identity tensor, and so this will go to a dependence on j alone, and j is nothing but det of f, and det f is related to the density, and so finally what we can conclude is that instead of this f, we can replace it by rho, which is the density. So that is the process here. So let us write this now. So basically we have that psi hat of f theta g f dot is equal to tau hat of f h theta g f dot of h, and then similarly for the other variables as well. So you will get that sorry, this should be psi hat. Then similarly tau hat of f theta g f dot is equal to tau hat of f h theta g f dot h, and so on. Okay, so same thing you write even for the entropy function and for the heat flux. So finally what you will get is that, so now this whole thing will imply that xi of f theta g f dot is equal to xi tilde of rho theta g and f. So f dot is lf. So that relation also we will use, and the dependence on f has reduced to a dependence on rho. So basically we can write this L in place of f dot. So we can now write the constitutive relation in terms of rho, theta, g and L for these fluids with short-term memory here. So let us write all the constitutive relations now. So let us just modify these constitutive relations which I have written here in the light of this definition of a fluid here. So this can be now written as xi tilde of rho, theta, g and L. This can be written as tau tilde of rho, theta, g and L. This can be written as eta tilde of rho, theta, g, L, and this can be written as q tilde of rho, theta, g, L. The other important thing to note is that in the case of thermoelasticity, we followed the Lagrangian picture, because as I said that for problems in solid mechanics, it is more convenient to work with the Lagrangian system. But in this particular case, we will prefer to work with the Eulerian system here. So that is why, see, all these relations that I am writing are defined on the deformed configuration. So we are now going to use the Cauchy stress and so on and so forth. Okay, so now we are in a position to write the theorem which will list all the restrictions on constitutive relations for a fluid. So theorem. So assuming continuous with respect to L, the necessary and sufficient conditions that every admissible thermodynamic process obey del line by del T plus theta dot minus 1 by rho tau L plus Q dot G divided by theta is less than or equal to 0. So this is the Clausius-driven inequality. So the necessary and sufficient conditions that every admissible thermodynamic process obey the Clausius-driven inequality are, so one is that the response functions psi tilde and eta tilde are independent of the temperature gradient, independent of the temperature gradient. So that is G and also L. So that means we will get that psi is equal to psi tilde of rho theta, and similarly eta is eta tilde of rho theta. And 2 is that eta tilde of rho theta is equal to minus del I tilde by del theta evaluated at rho theta. And the third thing is that the equilibrium stress defined by tau tilde naught, so tau tilde naught of rho theta is equal to tau tilde of rho theta 0 0. So basically, whatever is the value of the stress tensor that is achieved by putting the temperature gradient to 0 and the velocity gradient to 0, that we are calling as the equilibrium stress. So this equilibrium stress is given by tau tilde naught of rho theta is equal to minus P of rho theta times I. So this P is what is known as the thermodynamic pressure here. So this P is the thermodynamic pressure. And this P is given by here. So P is equal to rho square times del I tilde by del rho of rho theta, or you can also write it in terms of the specific volume. So P d theta is equal to minus del I tilde of if you express it as a function of V. So this rho is 1 by V. So V is this 1 by rho. So this is in terms of the specific volume, you can express it as this particular derivative here. And the last condition is that the extra stress, okay, so that is the viscous stress, so to speak, is the satisfies an inequality. So let us write that particular inequality also. So 4 is that the extra stress, or viscous stress, defined by sigma tilde of rho theta gl is equal to tau tilde rho theta gl minus tau naught of rho theta satisfies sigma tilde times rho theta gl matrix inner product D plus 1 by theta naught, 1 by theta, sorry, q tilde of rho theta gl matrix dot product with G is less than or equal to 0. Okay, so this is the this is known as the dissipation, general dissipation inequality. This is known as a general dissipation inequality. So you can see that this inequality, so in the case of thermoelasticity, we saw that this inequality involved only the heat flux and temperature gradient, but in this particular case, this also involves now viscous stress. Right? So we know, right, from fluid mechanics that viscosity is like friction, right, and that generates a dissipation within the fluid, right, and so it is not at all surprising that you have the viscous stress along with the matrix product of the rate of deformation tensor that is also appearing in this generalized dissipation inequality. So individually we cannot say that this part is greater than 0, and individually we cannot say that this part is less than 0. So as as a combination, this whole thing has to be less than or equal to 0. So that is the conclusion of this. So these are the conclusions that come out of this theorem here. So basically these are the restrictions that are imposed by the second law of thermodynamics. So now let us try to prove this particular theorem. So the proof is going to be very similar to what we did in the case of thermoelasticity. So we will construct a process, a general a thermodynamically admissible process, and again we will be able to get arbitrary values for variables like L, F, rho, theta, and so on, and then we will use that arbitrariness in order to draw our conclusion. So as I said, this process is very, very similar to what we did in the case of thermoelasticity. So okay, so let us start this whole process now. So proof. So again, use the chain rule basically. So we have del xi by del t plus theta dot minus 1 by rho times tau times L plus q dot g by theta is less than or equal to 0. So use the chain rule on this. So you will get that del xi tilde by del f times f transpose minus tau tilde by rho matrix inner product L plus del xi tilde by del theta plus theta tilde times theta dot plus del xi by del g times g dot plus del xi by del L times L dot plus q dot g by rho times theta is less than or equal to 0. So here actually, although now we have seen that the dependence on F reduces to dependence on rho, we have already said that, but in the beginning I will not use that reduction. I will use that reduction at a later stage. So basically whatever analysis that I will go through will also be valid for a viscoelastic material. So that is the reason that I am keeping it. But when we specialize to the case of a fluid, achieved, the dependence on F can be reduced to a dependence on rho, and then that will lead to a further simplification of the results. But as I said, that I will just keep the F as it is and the L as it is, as I said, that so that whatever I am developing is also valid for a viscoelastic material. Okay, so given now, so we will construct the process, thermodynamic process, admissible thermodynamic process, such that we will give the arbitrary values of these tensors here, which are involved in this analysis here. So given F diamond, theta diamond, G diamond, L diamond, then A diamond belonging to limb, then alpha belonging to R, then A belonging to R3. There exists an admissible thermodynamic process where theta of x in diamond is equal to theta diamond, then G of x diamond T diamond is equal to G diamond, then L of x diamond T diamond is equal to L diamond, then F of x diamond T diamond is equal to F diamond, theta dot of x diamond T diamond is equal to alpha, then G dot of x diamond T diamond is equal to A, and F double dot of x diamond T diamond is equal to A. So this is it. So again, these variables are arbitrary, okay, and then we will use this arbitrariness in the proof, just like we did in the case of thermoelasticity. But while assuming that these arbitrary variables, we have to first see whether we can construct a process where these arbitrary variables can be achieved. Only then can we use it. So suppose if there is no process where these arbitrary variables can be achieved, then we cannot assume these variables to be arbitrary, right? And so that is the reason that it is important to make sure that all these arbitrary variables can be achieved in an actual thermodynamic process. Okay, so that is so let us show that such a process exists. Yes. So determinant of F diamond plus T minus T diamond times L diamond F diamond plus half of T minus T diamond times A is greater than 0, and and also theta diamond plus alpha times T minus T diamond plus F diamond transpose times G diamond plus T minus T diamond times A plus L diamond transpose times G diamond times X minus X diamond is greater than 0. So if we take, so we know that determinant of F diamond is greater than 0 because we are choosing F diamond to belong to limb class. So if you take T sufficiently close to T diamond, right, then by the continuity arguments, we can say that the determinant of this entire thing is greater than 0. And similarly, if we take T sufficiently close to T diamond and X sufficiently close to X diamond, then this whole thing will also be greater than 0, because so this will represent the absolute temperature in the process that we are going to consider, and this is going to represent the deformation gradient of the process that we are going to construct. And so that is the reason that we need to ensure that the conditions, that det F greater than 0, the orientation preserving condition, and the fact that the absolute temperature is greater than 0, those conditions should be satisfied. Right? So that is why we have this. And now we will construct the process. So chi of x comma t is equal to f diamond plus t minus t diamond times L diamond f diamond plus half of t minus t diamond square times a times x minus x diamond times x minus x diamond, and theta of x comma t is equal to theta diamond plus alpha times t minus t diamond plus f diamond transpose times g plus p minus t diamond times a plus L diamond transpose times g diamond dot of x minus x diamond. So if you look at these two processes now, then you will see that this now leads to this one. So for example, let us just evaluate at x diamond t diamond. So this one will go to 0, correct? This term will go to 0. So you will get theta diamond. And so you can verify that. So for example, the deformation gradient, right? F is equal to f diamond. So the deformation gradient will be given by whatever is there in the square parenthesis here. And then at t equal to t diamond, you will get f diamond, and that is this term here, and so on and so forth. So you can just verify that these two processes will give the arbitrary quantities that are required. So theta diamond is now arbitrary, except for the fact that it is greater than 0, but otherwise arbitrary, and so on. This g delta is arbitrary, L delta is arbitrary, f delta is arbitrary, and so on. Okay, so now we are able to achieve arbitrary values of these tensors by constructing these two processes. So there exists a process such that these arbitrary quantities can be actually achieved. So that is very, very important. And then of course then the deformation gradient has to meet this restriction. So that restriction is also met, and the absolute temperature has to meet this restriction. So this absolute temperature is nothing but whatever I have written here. So that restriction is also met, because if you take t sufficiently close to t diamond and x sufficiently close to x diamond, then these conditions are satisfied by continuity here. So basically now we can achieve arbitrary values of these variables here. So now let us write the Clausius-Duhem inequality by applying the chain rule now, and then see what the implications are for that particular thing here. So now the Clausius-Duhem inequality can be written as now, and so del xi tilde by del f evaluated at rho diamond, theta diamond, g diamond, L diamond times f diamond transpose minus 1 by rho diamond, now tilde of rho diamond, theta diamond, g diamond, L diamond times L plus del by del theta of xi tilde of rho theta g L plus theta tilde of rho theta g L times alpha plus del by del f of tilde rho theta G L matrix inner product A plus del by del G of xi tilde of rho theta G L dot with A plus 1 by rho theta times Q tilde of rho theta G L dot G is less than or equal to 0 here. So all I've done is that I have used the chain rule now. So because xi is a function of f, rho, g and l, so I'm just writing it as del by del f times l this and so on. So just this is all a simplification of after applying the chain rule here. And now all the variables here that or whatever are listed here, all those variables are arbitrary. So if the conditions which are stated in the theorem are satisfied, then you will see that automatically this inequality is satisfied, right? So the sufficiency of those conditions is quite trivial. So the important part of the proof is to show that those conditions which are stated in the theorem are necessary, right? So because we have seen that they are necessary and sufficient conditions, so now we have to show that those conditions are necessary as well. So so let us now simplify this inequality and see what we get here. So okay, so use now. So use arbitrariness of F diamond, theta diamond, G diamond, L diamond, and A, then alpha and B. Okay, so we use the arbitrariness of all these variables to show the particular result here. So if you look at this inequality now, that can be written as del xi tilde by del f dot of rho theta G diamond L diamond matrix inner product A plus f1 of f diamond theta diamond times G diamond L diamond alpha A is less than or equal to 0. So if we now fix, so again fix these values, so fix these values here, these values, so then this becomes a constant. So this procedure is again very similar to what we did in the case of thermoelasticity. So we can write now this as del xi tilde by del f dot of rho theta G L matrix inner product A plus C. So this C is just a constant here. So is less than or equal to 0. Right? And then as I said that this C constant does not depend on A, and so even if you let this term dominate C, and then you can switch the sign on A, right? And so this inequality will be violated unless this term is equal to 0, right? And so this will imply, so basically this will imply that del xi by del f dot of rho theta G L is equal to 0. So that is the conclusion that you will get from this particular result here. Okay, then let us see. So yeah. And we also know that f dot equal to LF, and so we will also get del by del L of xi tilde of rho, theta, g, and L is equal to 0. So basically what we have shown is that the free energy is now independent of the velocity gradient. Okay? Then, so the next thing we will consider is del xi tilde by del g evaluated at rho, theta, g, and L dot with A plus F2 times F diamond, theta diamond, G diamond, L diamond, alpha is less than or equal to 0. Now again, same thing, right? Now we fix these quantities here. So fix these quantities, and so you will get that del xi tilde by del g of rho, theta, g, and L is equal to 0, correct? And so basically, because this is a constant, again, let this term dominate the constant, and then you can switch the sign of A to get a violation of this inequality, and the only way that you can prevent the violation of that inequality is provided this term is equal to 0, correct? And so we are using the arbitrariness of all these variables in order to show these various conclusions here. So basically now what we have shown is that the xi tilde is independent of the velocity gradient, and it's also independent of the temperature gradient here. So this implies now that del xi tilde by del g is also equal to 0 here. So let me just summarize the conclusion that we have is that now we'll have that xi is equal to xi tilde of rho, comma t. So this is the conclusion that we have, and so again the next thing that we will consider is del xi tilde by del theta of rho theta plus eta tilde of rho theta g and L times alpha plus F3. Now let us take it as F diamond, G diamond, theta diamond, G diamond, and L diamond is less than or equal to 0. Again, fix all these variables. So fix this, and so this is again a constant. Same thing again. Alpha is arbitrary. And then the arbitrariness will lead us to the fact that eta tilde is minus of this one here. So now we will get that eta tilde of rho comma theta is equal to minus del xi tilde by del theta of rho theta. So automatically we will see that because the entropy is now a gradient of the free energy, and because the free energy depends only on rho and theta, automatically the entropy will also depend only on rho and theta. So that means the entropy is independent of the velocity gradient and the temperature gradient. And so oftentimes we will hear this statement in books on thermodynamics and fluid mechanics that the entropy is a state function of the density and the temperature. So this is a proof for that even if you assume the entropy function to depend on the velocity gradient and the temperature gradient, we can show by thermodynamic considerations that they are independent of the velocity gradient and the temperature gradient, and that it is indeed a state function of the density and temperature. So oftentimes in the thermodynamics books they may have come to this conclusion through experimentation or whatever, but it is never rigorously proved. So now within this framework of the Clausius-Dion inequality, one can give a rigorous proof of the fact that the entropy is a state function. And so similarly the specific energy is also a state function of the density and temperature, because that is just simply eta is E plus xi theta, and so even the internal energy, the specific internal energy, is also a state function of the density and temperature. So all these conclusions which are sort of not proved in a rigorous sense cannot be proved very rigorously within this framework. We will consider the remaining implications of this particular inequality in the next class, because that is slightly complicated. So we are going to split the stress tensor into an equilibrium part and a extra part, which is the viscous part, and then we will come to the fact that the viscous stress satisfies the generalized dissipation inequality. So that part we will do in the next class.